Right, let's get started. So, hello everyone, this is SeungryongKim. So, this is lecture 7. So, in this lecture, we discussed what is matrix operation and what is the inverse of matrix, right? Today we will finish chapter 2.3 and we will move to the matrix factorization, lecture 6, right? And before that, I have one notification. We will have a midterm exam, right? So midterm exam will held in April 28 from 5 p.m. to 7 p.m. The location is 애기능 Stunt Center 301 and 302. Yeah, you're allowed to bring one A4 size cheating sheet, both sides, but any electronic device are not allowed. Okay, please bring your student card to check your attendance. Okay. 자, 우리 한 번만 더 강조할게요. 우리 중간고사 있어요. 오늘 다시 공지메일 보냈고요. 우리 4월 28일 5시부터 7시까지 있을 거고, 애기능, 한국말로 하면 애기능 생활관, 혹시 2학번 학생들은 한 번도 안 와봤을 수도 있을 것 같은데, 애기능이라고 있어요. 저기 동그랗게 생긴 건물이 있고, 애기는 301호와 302호에서 나눠서 볼 겁니다. 알겠죠? Question for our midterm exam. No? Right. Today, let's start characterization of matrix here. So far we discussed the matrix. Okay, let's recap. Last Monday we discussed what is the matrix inverse, right? So yeah, the inverse of matrix A is uniquely determined by A inverse A to the -1, 그쵸? Yeah, we discussed how to compute the inverse of matrix A 2x2 case, but it's not general case. So in general n by n matrix, we need to wait to find out inverse of matrix A, right? So before that, would like to discuss Ax equals B has a unique solution as X is equal to X inverse times B, 그렇죠? Like this. Then how to find out matrix inverse here. So this is theorem 7. So if A is M matrix A is invertible, if and only if matrix A is row equivalent to the identity matrix, in that case, any sequence of elementary law operations that reduce A to the IN also transform IN to the inverse of matrix A, right? So how to use this technique to find out inverse of matrix A looks like this. So row reduced augmented matrix AI, then A will be row reduced to the identity matrix, then there exists the invertible matrix A inverse, then I will be transformed to inverse of matrix A, right? So here was the example, how to find out inverse of matrix A, which was a 3x3 case. Then first of all, we said that this kind of augmented matrix, then row reduced, blah, 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 blah. Then if A part, 3x3 part, was reduced to the identity matrix, then this one is inverse of matrix A, right? So this here, right? So today we will continue characterization of the invertible matrix. Right. So this is the theorem 8. Theorem 8. Yeah. So this theorem 8 provide a review most of concepts introduced in chapter 1 and chapter 2 in relation to the system of n-linear equation in n unknown. So it can build n by n matrix. Then we will check when this matrix A is invertible or not. This is theorem 8. So let A be a scalar n by n matrix, then the following statement are equivalent. That is, holder statement are either whole true or whole false, right? this is invertible matrix theorem. So, first of all, matrix A is an n by n matrix, then A is an invertible matrix. A is rule equivalent to the n by n identity matrix. A has n pivot position. Equation Ax equals 0 has only trivial solution. Columns of matrix A form a linearly independent set. The linear transformation x to the ax is 1 to 1. Equation Ax equals b has at least one solution for each b in Rn space. Columns of matrix A span Rn space. Linear transformation x to ax maps at Rn onto Rn. There is n by n matrix C such that CA is equal to I, AD is equal to I, and A transpose is an invertible matrix. For such a statement, hold true, either hold true or false. This is invertible matrix. For example, if you have arbitrary matrix A, then if the columns of your matrix A span Rn space, then you can say that your matrix A is the invertible matrix. Why we need to this kind of theorem, right? So let's suppose that you have a matrix equation Ax equals B, right? You have a matrix A, then you just analyze your matrix A, then you found that A transpose is invertible matrix, then A is invertible, then your solution of this matrix equation can be inverse of matrix A times vector B. Or, if your matrix A has an n pivot position, then your solution is going to be looks like this. So you only have, so you have this linear system has solution. So solution existence, then your solution can be unique. So that's why we have to know invertible matrix theorem. To prove this theorem, we need a long time to understand each concept, what is invertible, what is row equivalent, and pivot position, Ax equals 0, homogeneous system has trivial solution, or the independently, or the linear independently set, columns of span Rn space, something like this. So, first of all, to derive this statement, you have to be familiar with this kind of concept. I believe you are already familiar to this concept because you have many chances to understand this and you already saw homework yourself, right? So today I will just briefly prove this statement. So to prove this invertible matrix theorem, we will sequentially prove each statement equivalent, right? So we'll start from A. Then first of all, we will represent A to the J. If statement A implies statement J, then we can represent A to the J. So if statement A implies, right, let's do that. Statement A is true, then inverse of matrix A works for C in J. So A implies J. So if A is invertible matrix, then there is this like C. So this is the definition of the invertible matrix, right? Then A to the J. Then and next, so here to here. Next, J to the B and J to the D and D to the C. J, so if there is a C, looks like this, and T. Here, equation Ax equals 0 has only the trivial solution. Why? Because we have an inverse of matrix A, then by multiplying A inverse left hand side and right hand side, then it's going to be identity matrix. So x is equal to 0 vector, so we only have a trivial solution, right? And T2C, if we only have the trivial solution, we don't have any free variable. Free variable, then we have a ampere position, right? Please remember this shape, 그렇죠? If there is a pivot position, n pivot position, because this is n by n matrix, then there's no free variable, right? So T to the T implies C. T implies C. So J implies D implies D, T implies C. And if A is squared and n pivot position, then pivot must lies on the main diagonal, in which case the reduced echelon form of A is identity matrix. So in other words, if A is a matrix, if A is a scalar matrix and it has n pivot position, blah 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 here, right? So it, in this case, matrix A can be low reduced identity matrix, right? So C implies B. And if A is low equivalent to the n by n matrix, we already know that A is invertible and invertible matrix exists. So A to the B is true. So we can make a circle like this. It's very straightforward, right? Question so far? 자, 여기까지 너무 조금 당연하죠. 우리가 지금까지 배웠던 컨셉들을 여러분들이 완벽하게 이해했다면 여기까지 따르면 어렵지 않았을 거고, 지금 얘기하고 있는 건 어떤 comprehensive summary of the whole of the concept we discussed, right? 제가 얘기했던 걸 좀 약간 요약하는 거예요. 그쵸? 자, 여기까지 이해했죠? A가 어떻게 다른 스테이트먼트랑 연결되는지. 그쵸? Question. Is that clear? No? Maybe yes? Right? Let's move. Okay, let's move to the following. Next, A to the K, because A inverse works for D. 그쵸? Here, if this one, by definition, 그쵸? There exists D. Then K to the G. K implies G, G implies A. What was the G? This one. Equation Ax equal B has at least one solution for each B in Rn space. Why? If we multiply inverse of matrix A to left hand side, 그쵸? Left hand side. Left hand side. A. Wait. K to G. Like this. A, T, B. Okay, so let's suppose A times B, T times B. Then it's going to be I times P. So it's going to be B, right? Then this one is going to be A times T times B, which is the P, okay, which is P. Then in this case, X is a T by P. So we already know T is inverse of matrix A, right? So this statement true, at least one solution. In fact, the exact statement, there exists unique solution. By definition, right? So K implies G. And what else? G implies A, right? So in this case, A is invertible, right? K, G. So in this case, 자, A to K is true, K to G is true, G to K is true. So K and G are lined to the circle. Looks like this. 그쵸? Further, G, H, I are equivalent for any matrix. G, H, I are equivalent. G, H, I. G, H, I are equivalent. 그쵸? AX equals B has unique solution. Column matrix A span Rn. Linear transform A X to AX math Rn onto Rn. Right? We already discussed this one in previous theorem. By theorem 4 and theorem 12a. Please check that. We already proved this concept. First, H, I are linked through the G to the circle. So here's G and G, H, I linked to the G. No. H, I are linked to the G here. One more thing is that T is linked to the circle. Where is D? 그쵸? The equation AX equals 0 has only trivial solution. So E and F are linked to the T. So because the T, E, F are equivalent, T, E, F. D equation AX equals has a trivial solution. E columns of matrix A form a linear independent set. D, E 뭐였죠? D, F. F here. Linear transformation AX to AX is 1-to-1. Here. They are whole equivalent. Why? We already proved this one in theorem 12b and section 1.7. So please check that. Anyway, T, E, F are all equivalent. So T, E, F are all equivalent. Finally, A to I and I to A, L, L이죠? A to L and L to A true. Why? Because if A is inverter matrix and A transpose is an inverter matrix, by properties of inverter matrix, let me show you here. Where's the here? So due to these properties, if A is invertible and A transpose is also invertible, right? So it's also true. Then A to the L and L to the A, A to the L, L to A. So because A is kind of anchor, then hold the statement equivalent, right? So that's inverter matrix here. This is one of the most important theorem in this semester. Okay. Question. So yeah, question was that if it's a 2x2 identity matrix, then it is 1001. 1001. 그쵸? You mean 10 means one first column, right? Then yes, 1001, right? Any other question? Because this is a very, very important theorem. So if you are not clear or if you want to some high level understanding, please let me know now. Very, very important. 자, 여러분 여기까지 좀 중요한 theorem이었고 아마 이 theorem이 여러분들이 지금까지 오면서 많은 개념들을 배워오는 거가 좀 이걸 왜 배우지? 약간 했던 것들을 하나로 엮을 수 있는 좀 재밌는 theorem일 거예요. 그렇죠? 결국에 무슨 얘기를 싶은 거냐? 인버터블이라는 개념, 피벗이라는 개념, 리니어 인디펜던트라는 개념이 뭐 컬럼 뭐 이런 것들이 하나로 다 원투원까지 하나로 다 연결될 수 있는 너무너무 중요한 개념이었고 이게 이제 인버터 매트릭스 theorem이라고 불리는 theorem이죠. 자, 질문. No? No? Okay. Then let me show you one of the example how to use inverter matrix theorem. Right. So you have a matrix A. The question is decide if matrix A is invertible or not. So in this example, we will use inverter matrix theorem. So there are so many kinds of statements in inverter matrix theorem, so you can use one of them. Okay, so in this example, I would like to use Stephen C. Stephen want to see here. We want to check the n pivot position. So first of all, okay, you have a matrix A, and you can reduce this matrix A to the EF form. Then you find that you can draw the pivot position here and here and here. So matrix A has 3 pivot position, hence it is invertible by inverter matrix theorem statement C. So that's one of the examples to use inverter matrix theorem. Okay. Then you can say looks like this, right? So your linear system, for example, is 0, 1, 3, -5, 0, 1, -1, -2, -2, 9, and you have a matrix vector x, which was x1, x2, and x3. And for example, your vector b looks like this, right? So without considering vector b, by just checking matrix A, which is invertible or not, you can just find the solution of your linear system by A inverse times B1, B2, B3, because matrix A inverse A is invertible, right? So that's a way to lose this inverter matrix here, right? Right. So one more straightforward statement that let A and P be square matrices. If AP is identity matrix, then A and P are both invertible with P is equal to inverse of matrix A and A is equal to inverse of matrix B. We can easily prove this one, right? All right. So AB, if AB is equal to identity matrix, then by multiplying inverse of matrix A, left-hand side to right-hand side, inverse of matrix A times AB, which is equal to inverse of matrix A times I. So which is the identity matrix? Then P is equal to inverse of matrix A. Or from the AB is equal to B, if we multiply inverse of matrix P, left-hand side and right-hand side, and AB, P inverse is equal to identity times P inverse, then because this is identity matrix, A is equal to P inverse. So here and here, right? So this is inverse. This is another statement. They are warning that inverter matrix theorem applies only to square matrix, so and by M square matrix. For example, columns of 4x3 matrix are linearly independent. We cannot use inverter matrix theorem to conclude anything about existence or non-existence of the solution of matrix equation of AX equals B, because it's not a square matrix. So we cannot use inverter matrix theorem. Please be careful. Right. Any question? No? Okay. Then let's talk about invertible linear transformation. In fact, we already discussed linear transformation can be represented by matrix B, standard matrix B. Standard matrix A. So it's just about inverter matrix A. 그렇죠? inverter matrix A. Anyway, you can think inverter linear transformation similarly. Okay, we already know matrix multiplication corresponding to the composite of the linear transformation in A times B case. 그렇죠? Then when matrix A is invertible, equation A invertible AX is equal to X can be viewed as a statement about linear transformation. In other words, right? So from X in arbitrary space, if we multiply A, we can move to the AX space, right? Then if we multiply A inverse again here, it's going to be A inverse times A times X, right? Then we already know this is just the X space, so these two spaces are same, so we can redraw this one as it looks like this. X is here, multiplied by matrix A will be transformed to the AX, which will be transformed again by A inverse, looks like this. So this is an invertible linear transformation. One more thing is that linear transformation T Rn to Rn is said to be invertible if there is a function S Rn to Rn such that STX is equal to X for all X in Rn space, or TSX is equal to X for all X in Rn space. Right? It's very easy, right? We already know there are standard matrix A for this one, so maybe function S is going to be inverse of matrix 3, right? So then we can easily say that inverse of matrix A, I, and in A times inverse of matrix A is I. Then we can say that STX is equal to X, TSX is equal to X for whole vector X in Rn space. It's very straightforward. Right. So finally, let transform T from Rn to Rn be the linear transformation. Let B is a standard matrix for T. 그렇죠? Then T is invertible if and only if matrix A is an invertible matrix. In the case, the linear transformation S given as A as A inverse X is the unique function satisfying equation 1 and 2. This is the equation 1 and 2. Unique function. Why? We already know inverse of matrix A are unique, right? Inverse of matrix A is unique. So this statement is also true. This theorem is also true. Right? Question. So in this chapter 2.1 and 2.2 and 2.3, we discussed the inverter matrix, how to compute the inverter matrix, and what is the properties of the inverter matrix, and we derived inverter matrix theorem in chapter 2.3. Right? That's it. Then today we'll move to the matrix factorization. This is chapter 2.5. Chapter 2.5, matrix factorization. Alright. Before that, we have two more notification. It's not a new notification. Portable homework 3 is announced in Blackboard, which is due to April 21, maybe next week, same time, 그렇죠? Before our class. And midterm exam, our midterm exam, I already announced this midterm exam, 그렇죠? Right. Let's move to the matrix factorization. Question. 자, 여러분 이제 여기까지 얘기했고 우리 이제 새로운 또 챕터로 넘어갈 건데 제가 얘기했던 컨셉들이랑 다르진 않을 거예요. 근데 팩토라이제이션이라는 얘기를 좀 할 거예요. 자, 조금 이제 넘어가기 전에 여러분들 한번 질문을 좀 들어보고 싶은데 잘 따라오고 있나요? 어때요, 여러분들? 할만해요? 지금 우리가 이제 2주 후에, 지금부터 정확하게 2주 후에 이제 우리 시험 보죠? 여러분들 조금 한번 수준을 보고 싶은데 어때요? 어려워요? 아니면 따라올 만해요? No opinion, right? 할만합니까? No opinion, right? 그쵸? 아주 훌륭합니다. Right. Today, okay. Today, let's move to the next chapter, matrix factorization. Right. So, what is factorization? So, what is the factorization? Factorization of matrix A is an equation that expresses matrix A as a product of two or more matrices. Right. So, in previous lecture, we discussed how to compute matrix multiplication B times C, which is a new matrix A, right? So this kind of statement also called synthesis, but factorization defined looks like this. We want to decompose matrix A to the product of a two matrix or the more matrix, for example, B times C. So why we have to know this? Because we want to analyze our matrix A. In other words, we want to analyze our matrix A in case that A is equals B. In other words, we want to analyze matrix A to the BC, for example, BC, then our new factorization matrification is going to BCX is equal to B. Maybe this kind of representation is much easier to understand your solution. That's the reason you have to know factorization. Right. So, more specifically, we will talk about LU factorization here, but in remaining semester, we will see many other factorization techniques, but today we will start just LU factorization. LU factorization. Okay, so LU factorization is motivated by the common industrial or the business problem solving the sequence of the equation AX equals B1, AX equals to B2, AX equals to BP, something like this. In many industrial or business problem, we want to solve this kind of sequence of equation. Looks like this. So with this vector x, we have an arbitrary transformation matrix A that generates B1, B2, BP. Then we want to find out solution X that satisfies this statement, this condition, right? First of all, if A is invertible, right? One could compute inverse matrix A, then compute inverse matrix A times B1, inverse A times B2, something like this, so on. However, it is more efficient to solve first equation. This is first equation. So first equation one by row reduction algorithm to solve this one, and obtain LU factorization of matrix A at the same time. Thereafter, the remaining equation, this one and this one, can be solved with LU factorization, which is going to be more efficient compared to the compute inverse matrix A. That's the topic of LU factorization. So assumption in LU factorization, A is m by m matrix. Maybe m is equal to n or not. That can be row reduced to the echelon form, yes, right? Without any row interchange, right? So So far, we discussed the row operation algorithm, which was the replacement, right? Replacement or interchange and scaling. So there was 3 kinds of row operation. Scaling, 그쵸? But one of the assumptions is that in this row reduction algorithm, we do not require the row interchange, which is the one constraint, but which will be generalized later. So then we can apply our LU factorization to any kind of matrix A, right? So please remember that. And what is the LU factorization? So LU factorization matrix A is written as A is equal to L and U, L and U, L and U. A is arbitrary matrix and L and U. L in this case, right? So first of all, A is M by M matrix, and L is M by N unit lower triangle with ones on the diagonal. So first of all, matrix L is M by N space and looks like this. Ones on the diagonal and this lower triangle part are non-zero value, but it can be zero value. Anyway, looks like this. Shape is looks like this. And U is M by N echelon form of matrix A. U is M by N echelon form of matrix A. So U is echelon form of matrix A. Looks like this. Maybe this is a pure position and this is non-zero vectors here. This is L and U. You can easily understand LU factorization, right? Because this matrix shape it looks like L, and this matrix is the echelon form, right? So LU factorization. This is definition of LU factorization. So in the later, we will talk about how to factorize original matrix A to the L and U, which is going to be the efficient, right? Efficient to solve the AX equal B, right? We will see this one. But before starting how to construct L and U, we should look at why they are so useful. Why LU is the better way to solve AX equal B solution. Right. First of all, let's talk about AX equals B. If matrix A is invertible, maybe we can solve this system as X is equal to inverse of matrix A times B, right? Right? Then let's compare the complexity of this X is equal to inverse of matrix A times B and using LU factorization, right? If we know A is equal to L times U, AX equals B can be written as L times UX is equal to B. 그렇죠? LUX is equal to B, so LUX is equal to B. And then writing U for UX here, if we define UX as Y, then so in this case UX is equal to Y. So we can find X by solving a pair of equation, I mean two equations. First of all, Ly is equal to B, 그렇죠? Ly is equal to B, and then if we find out Y, then we can solve another equation, Ux times equal to Y. Ux equal times to Y. In other words, first solve Ly is equal to B for Y, and then solve Ux is equal to Y for X. So in other words, right, so here is X, here's B, then we want to find the f that multiply by a to the b here. This is just the solution by inverse of matrix A times B. 그렇죠? Rather than directly solve this equation, if we have LU factorization, we can factorize this tab, this linear transformation as multiplication by U and multiplication by L here. Why this kind of technique is useful? So, to understand this, please remember numerical note here. Each equation is easy to solve because L and U are triangular. Because L and U are triangular, looks like this, triangular, lower triangular and upper triangular. Here are numerical note. Please remember, please read this here, this one. But I would like to show you the one example why LU factorization is more useful. So, first of all, right. So you have a matrix A, looks like this. Let's assume that you already have L and U, matrix L and U that factorize this matrix A, right? Then use this factorization to solve AX equals B, where B is equal looks like this. So, what is our strategy? From previous slide, we will decompose this solution procedure as Ly is equal to P first and Ux is equal to Y, right? Okay, let's do that. First of all, let's solve Ly is equal to P first. Right. How can I solve Ly is equal to P? How can I solve Ly is equal to P? There are many possible ways, but let's use row reduction algorithm. Algorithm in matrix domain, right? Then first of all, let's make augmented matrix, which was L and which was P, right? Then how to solve this augmented matrix? We want to row reduce this one as a R, E, F form, right? And then we can say that this one is going to be the solution Y, because this is the earliest form, so we can directly know that x1 is equal to -9, x2 is equal to -4, x3 is -5, just 5, x4 is equal to 1, looks like this, right? So let's do that. So fortunately, we only have this term, because this is the definition of the L. So we don't need to care upper part, right? Then let's do that. So let's suppose that it's R1, R2, and R3, and R4. Then first of all, we want to eliminate this three term, as a zero. Then how can I do that? New R2 is going to be previous R2 plus R1. R3 is going to be R3 minus 2R1, and R4 is going to be plus 3R1, right? Then by using this row reduction, I mean the replacement, 그쵸? This is replacement. By using these three replacement technique, this matrix can row reduce to the 1, 0, 0, 0, 0, 1, -5, 8, 0, 0, 1, 3, 0, 0, 0, 1, and this is negative 9, and this one 5 plus negative 9 and 7 minus 2 times negative 9, and last term 11 plus 3 times negative 9. Then we can find out next next matrix, right? Then the next step is to apply the low elementary operation to eliminate this term and this term. Finally, this term. Then let's talk about complexity. Complexity, I mean the how many multiplication and addition is required to solve this kind of task. Okay, so here, and here, we require 3 multiplication and 3 addition, 3 addition. And similarly, to eliminate this one and this one, we require maybe 2 multiplication and 2 addition, right? And to eliminate this one, maybe we require 1 multiplication and 1 addition. Then to low reduce original matrix to LP to the this one RDF form, we require 6 multiplication and 6 addition, right? It's very easy. Then we find out y here, right? And then we want to know vector x. Then we have to solve ux is equal to y. We already know y, vector y, right? But interestingly, when you want to solve ux is equal to y, this interestingly, this is a backward page of low reduction algorithm. Why? Here. This is the matrix U. This is the echelon form, right? Echelon form. We already know. Then y here. So it's exactly same procedure in backward page in low reduction algorithm. What was the backward page? We want to hold the pivot position as a 1 and eliminate this upper part to generate REF form. Then this part is going to be our solution x. So which x is going to be 3, 4, negative 6, negative 1. So to implement this, okay, so first of all, to eliminate this term and this term and this term, we require 1 division, one division and 3 multiplication and 3 addition, right? Why? Let's just assume that, okay, so this is R4, R3, and this is R4. Then, for example, new R3 is going to be the R3 minus R4, plus R4, 그렇죠? To understand this, negative 1 times negative 1 minus and minus 1. 그렇죠? So here was the 1 division and 3 multiplication and addition to eliminate these 3 terms, right? 그렇죠. Similarly, you have to eliminate this term and this term. Then finally, we require 4 division. So because there are 4 pivot positions here and 6 multiplication and 6 addition. Right. All right. Then we find the solution x is just 4, 3, 4, negative 6, negative 1. Right. So in this case, let's think of how many arithmetic operation. So arithmetic operation mean addition, multiplication. 아이고, 다시 쓸게요. multiplication, or division, something like this. This is arithmetic operation. So in this kind of the solving skill, to find the x, we use 28 arithmetic operation, which is also called the float point operation, excluding cost of the finding L and U. So in this case, we just use 28 arithmetic operation. In contrast, we will skip this one, but in contrast, if you row reduce AP directly to IX to find the solution X, it takes 62 arithmetic operation. If you don't believe this one, please do it yourself. But in this case, it takes about it takes 62 flops compared to the 28 flops in the LU factorization based solution, right? So that's why if you have L and U, you can easily solve. You can more efficiently solve your AX equals B. Question. 자, 그래서 여기 한국말로 한 번만 더 설명할게요. 그래서 이게 무슨 얘기를 하고 있는 거냐 지금. 자, 우리가 LU 팩토라이제이션이 이런 식으로 이렇게 아름다운 형태, L은 이렇게 생기고 U는 이렇게 생긴 형태로 표현하고 싶은 건데, 이제 이걸 A to A를 이런 걸 표현하기 전에 왜 이게 필요하느냐를 생각해보면 결국에 LU로 A를 바꿨을 때 훨씬 효율적으로 AX equals B를 풀 수 있기 때문이에요. 왜 그러느냐? 결국에 AX equals B는 사실 A가 LU가 되면 ly equal to b, ux equals y를 사실 시퀀셜하게 풀면 되는 거죠. 근데 ly equals b와 ux equals y가 이 매트릭스의 성질 때문에 정말 쉽게 풀어지기 때문인 거예요. 왜 그러냐? ly equals b는 사실 이 어퍼 트라이앵글에는 값이 없기 때문에 사실 얘는 없애면 돼요. 그러니까 금방 REF으로 바꿀 수 있고요. ux equal to y에서는 반대로 여기만 있어요. 그렇기 때문에 여기만 지우면 되니까 또 엄청 빠르게 REF으로 바꿀 수가 있고요. 그렇죠? 그래서 그때 계산되는 summation, 그러니까 addition이죠. addition, multiplication, division을 계산을 해보면 A, B를 다이렉트리하게 계산하는 것보다 훨씬 효율적이다 라는 거죠. 그렇기 때문에 우리가 electroization이 필요한 거다라는 거예요. 알겠죠? So this one is the numerical note why LU factorization based method is useful and more efficient comparing to the directly solving AX equal to B. Right? Right. Question. 정응? Okay, the question about decomposing L and U requires operation. Yeah, exactly. So it's now unpaired to directly compare 28 and 62. But even though we consider the complexity to decompose L and U, this kind of way is much more efficient. Okay. Professor, could you explain how to find? We did not discuss yet. We did not discuss how to find those matrix L yet. So from here, we will talk about how to find this. Okay? Question. I don't know why the process is called the backward page. Right. So to understand the backward page, you have to go back to our row reduction algorithm. Okay, so row reduction algorithm consisting of the forward page and backward page. So in backward page, we just to consider this kind of matrix, right? Why? This is echelon form of matrix A. 네? 그래서 에라우스의 기억을 해봐요. 우리가 로릭스 알고리즘에서 EF 폼에다가 RF 폼으로 가는 과정에서, 그쵸? EF 폼으로 가는 과정이 forward 페이지였고 EF 폼에서 REF 폼으로 가는 과정이 backward 페이지였어요. 그쵸? 그러니까 backward 페이지가 똑같다. 하는 거죠. right? question. LU는 다이고널 엔트리를 미리로 만들지 않기 때문에. The question was, okay. So before that, in LU factorization, we have to make this diagonal term as 1 in L matrix. Okay? Right. So from now on, let's talk about how to find the matrix LNU. But fortunately, we already know this is echelon form. Then we can imagine if we low reduce matrix A to the echelon form, maybe we can find out L and U. Right? This is starting point. So to understand this, we have to go back to elementary matrices. We already discussed this one in previous lecture, right? So what's that? There were three kinds of one: replacement, interchain, scaling, and we discussed the representative matrix E form here. 그렇죠? And one of the assumptions is that in LU factorization, we did not consider the interchain. So we are just assume that we don't need the interchain. So let's just assume that replacement and scaling. Maybe we can represent this elementary matrix as a E matrix E. And one more thing is that we already know inverse of matrix E, matrix E looks like this. If it is replacement elementary matrix, inverse of matrix elementary matrix E is equal to elementary matrix negative K. If interchain inverse of matrix E is matrix E itself, and scaling case inverse of matrix E is equal to elementary matrix of 1 over K. We will not prove this one, but we will just see why this statement is true here. For example, let's say that matrix A is 1, 2, 3, 4, 5, 6, 7, 8, 9. Then, first of all, let's suppose that elementary matrix for the replacement, for example, 1, 1, 1, 0, 3, 0, 0, 0, 0. So, from definition, we already know this matrix E 1, 0, 3, 0, 1, 0, 0, 0, 1 can make replacement on row 3 with 3 times row 1. Okay, let's do that. So if we multiply E times A, then it's going to be a 1, 0, 3, 0, 1, 3. And matrix A was 1, 2, 3, 4, 5, 6, 7, 8, 9. Then let's compute this one. Then first element was that compute by first row and first column. So it's going to be 1. And second element, this first row times second column, it's going to be 2, 3, 4, 5, 6. You can do that. And this term, it's going to be third row times first column. So it's going to be 3 times 1 plus 1 times 7. The next one is 3 times 2 plus 8. 1 times 8. And 3 times 9. 3 times 3 plus 9. Then it's a replacement operation by R3 plus 3 R1. by definition of the replacement elementary matrix. Then by definition, inverse of this matrix is defined like 1, 1, 1, negative 3, 0 looks like this. So from this one. Then let me check. This is the real inverse. To check that, we can do looks like this, E times E inverse. So it was 1, 1, 1, 0, 3, 0, 0, 0, 0. And the inverse of matrix E is 0, 1, 0, negative 3, 0, 1, 0, 0, 0, 1. Let's do that. Then, by definition of matrix multiplication, it's going to be 0, 0, 0, 0, 0, 0, 0, 0 here, and here, just in here, third row times first column, then it's going to be 3, negative 3, so it's going to be 0. So in other words, it's going to be identity matrix. So this is the inverse of matrix, elementary matrix for replacement case. We will use this property to derive L and U. Question. One more interesting properties of the replacement operation is that, okay, let's suppose that we have a sequential, okay, we apply sequential replacement operation, maybe E1, E2, and E3, which is defined like 1, 1, 1, 2, 1, 1, 1, 3, and 1, 1, 1, 4, remaining part are 0. Then you can easily see this matrix A, I mean the product of E1, E2, and E3, it's going to be 1, 1, 1, 2, 3, 4. You can easily prove that. You can easily compute that here. 2, 3, 4. This is properties of the replacement elementary matrix. And similarly, inverse of matrix A, it's going to be the inverse of the E1, E2, and E3. Then we already know inverse of the E3 times inverse of E2 times inverse of E1. Then by definition, this one is going to be 1, 1, 1, negative 4, 1, 1, 1, negative 3 here, and 1, 1, 1, negative 2 here. Then it's going to be finally 1, 1, 1, negative 2, negative 4, negative 3, and negative 4. Negative 2, negative 3. Right? So when you consider the sequence of product of the elementary matrix, the relationship of original matrix A and inverse of matrix A looks like this. Right? This is property. We will use this property to derive our LU factorization. Okay? Any questions so far? Any question? No? Right, time 6:04. Right. So today we will finish here, and next week we will continue how to LU factorize your own matrix A by using these kinds of replacement properties. Then we will see systematical way to derive LU factorization. Okay? Question? No? Right. So, okay, so there's a question. The question about why we did not use low interchange in this case. First of all, to derive LU factorization, if you assume there is an interchange, it does not work, right? So that's one reason. So that's why we first derive LU factorization without considering interchange. Then And then we can extend Euler factorization in case interchange, right? We'll see this one later. Any other question? 정우학생 질문 다시 정리하면은 Euler factorization 자체가 interchange를 고려하면은 정의가 안 되기 때문이라고 보면 돼요. 정의가 안 돼요, 바로. 그렇기 때문에 interchange 없다고 가정한 다음에 interchange가 있는 경우를 확장을 하는 식으로 이제 마지막에 배울 거예요. 알겠죠? Any other question? No? Right. So that's it. So this is end of this lecture. Maybe next week is the final lecture before the midterm exam. Please remember that. And please remember we have a homework 3, right, which is due on next week. So please try to solve the homework as early as you can. Right? No question? Right. Okay, so that's it. So this is the end of this lecture. Thank you very much and see you next week. 자, 여러분 오늘도 너무 고생 많으셨고요. 우리 다음 주에 보도록 합시다.